particular section, we will study what are atoms composed of. Atoms are composed of what are called as the subatomic particles. The term subatomic means that when you break an atom, you will find these three small particles. There are actually more than these three, but for our focus, we will only study the three subatomic particles. There are two particles that are present within the nucleus of an atom, and those are the protons and the neutrons. The protons and the neutrons are present right in the central, as shown over here, and the electrons are present around the central core. The central core is called as the nucleus. The region outside is called as the cloud region or the electron cloud. Why is it called as the cloud region? Because that's the location where the electrons can be found. Another important thing to remember at this stage is that all of these three particles have a unique charge. Protons always have a positive charge, and neutrons are neutral. So protons and neutrons are present in the nucleus, but the total charge of the nucleus would then be positive because neutrons do not have or do not carry any charge. Electrons that are present around the cloud are all negatively charged. So this is the information that's shown to you on the slide. Another thing that you can see over here is the size. If you compare the size between the protons, neutrons, and electrons, you will find that the electrons have a much smaller size. You can see this ball that is shown to you is much tiny or much smaller. So electrons have a smaller size compared to protons and neutrons. Over here it's shown to you that the two positive charges can repel, the two negative charges can repel. However, if you have positive and negative, they can attract. So the negatively charged electrons can be attracted to the nucleus, and that keeps it all intact or together because of the attraction between the opposite charged particles. Now, this is just an experiment that was carried on by Rutherford, and it's called his famous gold foil experiment, and in which he studied the charges of these particles. He pretty much aimed atoms. He was pretty much aiming beams to the atoms of gold. So you have a gold foil that is shown over here, and he beamed charged particles, and most of these will went through the atoms, and some would deflect occasionally. So with the different kinds of beams that he threw within this the atom foil, he was able to convince that, or come to the conclusion that the inside must be positively charged, because when he beamed positively charged particles, they repelled, and when he beamed negatively charged particles, they went through. So this is how he came to the charges that were discussed in the previous slide. So the structure of an atom thus will have protons, neutrons, and in the center, and the electrons on the outside. Now, each of these have a symbol. Protons have a symbol of P, as shown over here. Neutrons have a symbol of N, and electrons have a symbol of E. Now, the charges are again, as I mentioned earlier, protons have one positive charge, neutrons have no charge, and electrons have a charge of -1. This part, which is the mass, you can pretty much eliminate that. We're not going to go into this part, so I'm going to go ahead and cross it. The mass is important. All of these have, the protons and neutrons have one AMU. AMU is the charge that's given to. Okay, I'm going to open up another section because for some reason I'm not able to write in here. But again, I'm having difficulties in here too. So today's lecture is not going to have any writing. Okay, the one AMU is shown to you over here. So you just write 1, and the AMU stands for atomic mass units. So it's a it's a scale that is used to measure or to get the mass of protons and neutrons. However, notice the mass of the electrons is very, very small, very negligible compared to the masses of protons and neutrons. The location, as I said earlier, protons and neutrons are located in the nucleus and the electrons are outside. You must definitely know all the information that's present on this slide. Now, for each atom, there is something called as the atomic number. When you look at the periodic table, you will find a whole number that is written on the top of an atom's symbol. So, for example, this is the symbol for the atom sodium. Sodium has its own unique symbol, and it's called as Na. Now, the symbol of the atoms have nothing to do with the letters that they begin with. The symbols are pretty much one or two letter abbreviation of a representation of an element. The names of the symbols of the element are either based on the person who discovered it, or it can be from the location of where they were discovered, or it could be the properties of that element, it could be the color of that element. So there is no set rule for that. And in your lecture packet, or I've given you, there's an appendix 3 that I think there's a list that has that all the atoms and their symbols. So you must know those for this class. So sodium is in Greek is called as natrium, or in Latin, and the symbol of sodium is Na. Now, whenever you have two letters in a symbol, the first letter is always uppercase and the second letter has to be lowercase. So nobody should write sodium as Na, or I'm going to try to write, it's kind of hard not to write. So you can't write sodium as Na. This would be totally incorrect. So if you do that, if you write both with uppercase, I'm going to cross them out. It has to be one uppercase, one lowercase. So on the top of this symbol, there is a whole number that is shown over here. This whole number is the number which is the atomic number. The atomic number is the number of protons in an atom. So if you see the number on the top, it always represents the number of protons that an atom may have. The atom's atomic number, let's go and look at some of the atomic numbers that are present for other elements. For example, hydrogen, you have the letter number 1, so it has 1 proton. Carbon is present over here, and it has the symbol of C, and the atomic number on the top is 6. So that's atomic number, means that there are 6 protons. Copper has copper is over here, and it's kind of hard to read when I'm trying to do it on here. Here's your copper, and you can see the number on the top is 29, and it has number of protons 29, and gold is Au, and that has atomic number 79, so that would be the number of protons. So it's fairly easy. You're interpreting the numbers that are written on the top, and those represent the number of protons. Okay. Atoms in an atom, electrons in an atom are always equal to the number of protons. So this is a very important thing that you should remember. Atoms are always neutral. If you recall, the neutrons that are present in the nucleus had no charge in them. So the charge of an atom is always 0 only if you have the number of protons equal to the number of electrons. So for example, aluminum has 13 protons and 13 electrons, and the net charge is 0. So you have 13 protons, 13 electrons, and totaling to 0, and that would be the net charge on aluminum atom. So let's look at some of the other elements. Here's a list that I've dragged, in which we have hydrogen, nitrogen, chlorine, iron, and gold. The symbols are shown to you: HNCl, FeAu, and the atomic numbers that are written on top of their symbol is given over here. Now, the atomic number is going to represent the number of protons that are assigned. Notice that it's the same number. So if you have 26, it's going to be 26. However, next to each element, you also also find a mass number. A mass number is usually depicted on the bottom of the symbol, and the mass number is the total of the neutrons and electrons. So for example, on hydrogen, on the bottom you see that it's written as H. You see 1 on the top and you see 1 on the bottom. So this indicates, the 1 on the bottom indicates that it's the mass number, which is the number of protons that it will carry. Sorry, the number of the protons plus the total number of neutrons. But since the atomic number is also 1, so the number of protons are 1, and the only way you can have mass number of 1 would be to have absolutely no neutrons. So it has no neutrons. Nitrogen, on the other hand, has 14 written on the bottom as its mass number. So 14 means that the top number is 7. Notice that is the number of protons that are 7. So if the mass number equals protons plus the neutrons, and we know that the proton number is 7 for nitrogen, then neutrons would have to be 14 minus 7, and that would be 7. So it has 7 neutrons. Chlorine again has 37 mass number. Atomic number is 17, so that indicates that the atomic number or the number of proteins are 17. Electrons are also 17, but the neutrons would be the mass number minus the number of protons would give you the number of neutrons, and those are 20. I'm really talking slow here so that you can sort of write it down and it starts making sense to you. That the mass number is the total number of protons and the number of neutrons. If you already know the number of protons, then subtracting the number of protons from the whole number of mass number, you can depict the number of neutrons. So we'll probably pretty much practice these a few in the class too. So again, be prepared to talk about this when you come to class. There are, like every rule has an exception, so there's a little bit of exception up here too. Sometimes you find atoms of elements that have slightly different mass number. So for example, if I was to obtain all the magnesium atoms that are present in the world, you find that always you have a magnesium is going to be identified by the number of proton, and it's always going to be 12. But however, the mass number may be slightly different. You may get some that have few extra neutrons in them. Notice when we write down 25, it means that you must have 13 neutrons, and over here you must have 14 neutrons. So these variations of an atom are called as isotopes. Isotopes are very important for us in biological systems, especially like for example when you're going out to get a scan, whether it's a thyroid or an MRI or any kind of scan. They usually always use isotopes for that. Isotopes emit radiation, and that's why you're able to depict them. Now, one of the interesting things that you see over here is that you have the number 24 written on the top and 12 on the bottom. To make it more clear, when you write down isotopes, we usually flip from the customary way of writing, in which we have the atomic number on the top. This is usually to help you guide. If you see the smaller number on the bottom and the larger number on the top, then it's usually an isotope. Otherwise, it would be always the smaller number on the top and the larger number on the bottom. So atomic mass of an element, which is another term, is then averaged based on all different isotopes. So when you average all the masses of all the isotopes that are present of each element, then the average isotopes have what is expressed as atomic number. Sometimes we use atomic number for like mass number and we mean the same, but I want everyone to realize that their mass numbers and atomic numbers are slightly different. atomic mass of an element is always on the bottom, and it's always shown to you as a decimal. It doesn't mean that you have half a neutron or 1.5 of a neutron. It's only because the atomic mass is the mass number all averaged, and you get a fraction of a number. For our class purpose, we will always round this number off. So for example, if I ask you what is the atomic mass of the chlorine that's depicted over here, the answer would be 35, because it's less than half, so you will just drop it and bring it to a whole number. So now let's look at the symbols of element. Now we have here we have sodium written with the mass number on the top and the atomic number on the bottom. Always I tell students to sort of look at the size of the number. So for example, if I was to write something like magnesium, then magnesium could be written down with atomic number. Usually you will find most of the time atomic number on the top and the atomic mass on the bottom. Only if I was to write down magnesium as an isotope, I would put the mass number on the top and the atomic number on the bottom. So I tell my students to not worry about which one is which, as long as the most important thing is if you have two numbers, the one which is the smaller number is always going to be the atomic number. The atomic number always gives us the information about how many protons are present. The larger number would be the number of protons plus the number of neutrons. So you have the protons and the neutrons within the mass number, and this is P. So the number of N is always going to be, as you can see, you will have P plus N minus P to give you the total number of neutrons. So you must know how to find these. So we will take a break here and then go on to the last part of this lecture.